Assalamu alaikum wa rahmatullahi wa barakatuh. Okay, today in this video, inshallah, I will try to solve two examples. The first example is 224. Example 2.24. In this example, we have the sensor with an output from minus 2.4 volt to minus 1.1 volt. The signal conditioning circuit output is from 0 to 2.5 volt. So we need to design a signal conditioning circuit that has an input from minus 2.4 to minus 1.1 volt. The output of the circuit is from 0 to 2.5 volt. The first thing we usually do is to find the equation that relates the output to the input, which is usually a linear equation, a straight line equation, in the form of y is equal to mx plus b. Y is the output, x is the input, m is the slope, which is equal to the gain, and we need to find the constant b to satisfy the equation. So let's start with finding the gain m. Usually the gain m is equal to span of output over span of input. In this case we have 2.5 volt minus 0 over minus 1.1 minus 2.4. This is equal to 2.5 minus 0, it is 2.5 volt over minus 1.1 minus it is plus 2.4, and this is equal to 2.5 volt over 1.3 volt, and this is equal to 1.923. This is the gain of the circuit. Then we have the equation. Substitute instead of y the output, which is V out, equal to the slope, which is 1.923 times x in this case is Vn, is the input, plus b. How we can find b? We can find b by substituting one bond, either the initial bond or the final bond. So we can say in this example it's better or easier to substitute the 0 here. So the output is 0 equal to 1.923 times Vn in this case is minus 2.4 plus b. From this we can find b is equal to, bring this one to the other side of the equation, so it will become plus, this is minus 1923 times 2.4, and this is equal to 4.615. So the final equation is V out equal to 1.923 Vn plus 4.615. This is the equation that we need to implement. You have here, because we have a plus sign, this is the plus sign here, so it's better or direct. We can use a summing amplifier. So let's do it using summing amplifier. The summing amplifier, like this, we have, this is the amplifier, sorry, this is the minus, this is the plus, we have, okay, let's choose, this is VO, choose the resistors all 10 kilo ohm, 10 kilo ohm, 10 kilo ohm, and here the first input of the summing amplifier, this is ground. Okay, this is summing amplifier. Okay, so we can put here minus 1.9 to 3 Vn, and here we can put minus 4.615, because if you remember the equation that we derived or found earlier, this is the equation. So the first term is this is the first input, and the second term is this, which is the second input. This is the second input. Okay, but here it is a plus and here a plus, because the summing amplifier is inverting. There is usually a negative sign at the output, so we need this to be negative, and we have negative here. The gain is negative, then it will be at the end, at VO, it will be positive. Okay, so how we can get this minus 1.923 Vn? We can connect this terminal to another amplifier like this. This is minus, this is plus. This is we can choose this to be 19, for example, 3 kilo ohm, and this is 10 kilo ohm. Okay, so here if you put Vn here, then the gain is 19.23 kilo over 10 kilo. We will get minus 1.923 V times Vn. So the output here is minus 1.923 Vn. Just connect this point to this point. Okay, for the Vn. This is the first term. The second term here, we can apply, this is DC and is negative, so we can apply, for example, a minus 15 volt supply, and we can use a voltage divider. We can put 100 ohm here, and we can choose a variable resistor here to get a voltage here to have minus 4.615 volt. You can adjust this resistor to have a voltage of around 4.61 volt. So you can choose this to be 1 kilo ohm. We can find the R. This R, say that this is Rx. We can say 100 volt using voltage divider rule. Okay, voltage divider rule. Okay, we can say that 100 over 100 plus Rx times minus 15 volt, the supply, we should have minus 4.615 volt. From this we can find Rx. Rx is around 2 to 5.03 ohm. So we can choose a variable resistor of 1 kilo ohm like this, and adjust it carefully to have this resistor value, which is 225.03 ohms, to have a DC voltage of minus 4.615 volt, and connect this here. This should be connected to this point, and this point should be connected to this point. So this is the final design of our signal conditioning circuit. Okay, this is the first solution. We can have another solution, the same problem, using not a summing amplifier, using a differential amplifier. We can use a differential amplifier. In this case, we will use the same equation. V out is equal to 1.923 Vn plus 4.615. So in this case, because we are using a differential amplifier, you know, differential amplifier is like this. This is the differential amplifier. This is minus, this is plus. This is V out. We have this resistor RF, and this is RF. This is RI, and this is RI. Here, this one should be Vn. Okay, and we have a DC voltage here, DC. So Vn minus DC multiplies by the gain. The gain here, the gain of this differential amplifier is equal to RF over RI. So let's first have the gain. You have to notice that the gain of this amplifier is a common gain for both inputs, for Vn and for DC. And because of this, we need to have a common factor here. We can say this is 1923 Vn. We can take the gain as a common factor, 1.923 times Vn plus 4.615 over 1.923 between two brackets. So this is a common factor because we need both terms, both this one and this one, have the same gain, which is 1.923. In this case, this is equal to 1.923 Vn plus, divide this by this, 4.615 over 1.923. We will get around 2.4, around 2.4. So this one should be 2.4 volt. Okay, and this one, the gain RF over RI should be equal to 1.923. So choose RI to be 10 kilo ohm, RI to be 10 kilo ohm. So in this case, this one should be 19.23. This is kilo ohm and this is kilo ohm. So when you divide this by this, you will get this gain. Then this will be equal to 19.23 kilo ohm, and this is equal to 10 kilo ohm, and this is equal to 10 kilo ohm, and this is equal to 19.23 kilo ohm. You always in the differential amplifier, we have this resistor is equal to this resistor, and this resistor is equal to this resistor, to have a balanced circuit with a gain of RF over RI. So this is another solution. Okay, now we can go to the next example, which is example 2.25. Example 2.25. In this example, we have a temperature sensor, which is basically a resistor. Maybe it is an RTD or a thermistor. Okay, the sensor range, the sensor resistance range is from 280 ohms to 1060 ohms. This is example 2.25. So we have this sensor resistance range. The signal conditioning circuit has an output this is the sensor, the signal conditioning output is from -5 volt to +5 volt. So one way to do this, we can have an inverting amplifier. Okay, we can have an inverting amplifier like this. Okay, we can put the sensor here, RS, this the value of the sensor, and we can put a fixed resistor here, for example, say 1 kilo ohm. So, and a voltage, a DC voltage of 1 volt, for example, here. Then this is the plus sign. So this is basically an inverting amplifier. This is an inverting amplifier. Say that this is the voltage Vx here. The voltage Vx is equal to because it is an inverting amplifier, it is equal to minus Rs, the value of the resistance of the sensor, divided by 1 kilo ohm times 1 volt. So we can say Vx in this case is equal to minus, because we divide by 1000 ohm or 1 kilo ohm. So this is basically a 0.001 times 1 volt times Rs. So this is Rs. So the relation that governs the output to the input, in this case the input is the resistance, which is in the feedback here, a linear equation. Vx is equal to minus 0.001 times Rs. Then after that, the output of this inverting amplifier, we need to connect it to another circuit. Okay, so we can say Vx has a range. Of the range of Vx is equal, say 1 Rs is equal to 280 ohms. We have Vx is equal to minus 0.001 times Rs, which is 280 ohms, and this is equal to minus 0.28 volt. 1 Rs is equal to 1060 ohms. This is equal to Vx is equal to minus 0.01 again times 1060 ohms, and this is equal to minus 1.06 volt. So the range of Vx is from minus Vx has a range from minus 0.28 to minus 1.06 volt. So we need now to design the signal conditioning okay, to have the voltage from the output of the signal condition is from -5 to +5. So we need to find the equation, the straight line equation or the linear equation. We have the equation V out again is equal to M Vn plus P. M is equal to span of output over span of input, and this is equal to the output is from -5 to +5, so it is 5 minus -5 divided by the span of the input. Span of the input, in this case the input is the Vx range is from minus 0.106 volt, okay, to we have minus 0.28. In this case we have 5 minus -5, it is 10 volt over minus plus, which is minus 0.78, and this is equal to minus 12.82. okay, so this is the gain, it is minus 12.82. now we have the out is equal to minus 12.82 times Vn plus B. okay, substitute the first value, for example -5 of when the output is -5, the input is equal to minus 0.28. here we found the range, okay, minus 0.28. okay, this is minus 0.28 plus B. In this case B is equal to -5, this is -5, and bring this here, so this is will be plus, and we have minus here, so minus plus, so this will be minus 12.82 times 0.28, and this is equal to -5 minus 3.585, and this is equal to minus 858. This is the value of P. So V out is equal to minus 12 is this is the M value or the gain, Vn plus B, which is in this case minus 858. This is minus 58. This is the equation. This is the final equation. okay, we can do it using this equation. We can implement it using a summing amplifier. We can choose the summing amplifier like this. This is the minus, this is the plus, this is VO, this is the first resistor, this is the second resistor here, and this is ground. Summing amplifier, this is the summing amplifier. So choose, this is to be 10 kilo ohm, this 10 kilo ohm, so the gain here is 10 kilo, so we can choose this 8. This is the value of P. and we have Vn here. This is DC term, and this is Vn. The gain should be, because Vn is multiplied here, Vn is multiplied by minus 12.82, so we can 10 kilo over R, 10 kilo ohm over R should be equal to 12.82. From this we can find R to be 10 kilo ohm over 12.82, and this is equal to 781 ohm. This R to have the gain of 12.82. Okay, so this is the summing amplifier that can satisfy our equation. But Vn in this case, this Vn comes from where? Actually from Vx, from the previous equation, from the previous circuit. This is Vx. This is Vx. Okay, this Vx here should be connected to this Vn. This is a solution of this example. Also, we can solve this equation using Wheatstone bridge. Instead of putting the sensor in the feedback of an inverting amplifier, we can put the sensor in one branch of the Wheatstone bridge. Let us do the second solution. Using Wheatstone bridge. Okay, the Wheatstone bridge here. This is the Wheatstone bridge, and we can put a supply voltage. This is DC bridge. We can choose all resistance here to be 280 ohm, 280 ohm, 280 ohm, and here the resistance RS of the sensor, because the sensor range is from 280 ohm to 1060 ohm. So we can start from to choose all resistance, other resistance to be 280 ohms. In this case, when we have this initial value of the sensor, then we get delta V here between point A and point B to be 0. So 1 RS is equal to 280 ohms. Delta V is equal to VA or VB minus VA. This is positive and this is negative. In this case, this is 280, 280, 280, 280 voltage divider rule. The voltage here is say that this is 10 volt. The voltage here is 5 volt, because it will be divided equally between two resistors, and the voltage here is also 5 volt, because it will be divided again equally between these two equal resistors. So 5 volt minus 5 volt, and this is equal to 0. Now we need to find the voltage delta V when the resistor is equal to 1060 ohm. Okay, when RS is equal to 1060 ohms, what is delta V? Delta V is equal again VB minus VA, and VB is equal to 1060 ohms over 280 ohms plus 1060 ohms times the voltage, the excitation voltage or the supply voltage, which is in this case is 10 volt. minus VA. VA is fixed. The voltage here VA is fixed. It is 5 volt because both resistors are equal. But here is changing. The voltage is changing. It will start from 5 volt, but because this resistor is changing from 280 to 1060, when this resistor is 1060, using voltage divider rule, it is 1060 divided by the sum of these two resistors times the excitation volt. We can get the voltage at B, but the voltage at A is fixed at about 5 volt, exactly 5 volt. So we can now have minus VA. VA is 5 volt. Okay, we can calculate this to be 7.9 volt minus 5 volt, and this is equal to 2.91 volt. So the range of delta V, is from 0 to 2.91 volt, and we need the output range from minus 5 to plus 5 volt. So what is the in this case the equation? We need to find the equation. In this case, V out is equal to MVN plus B. M is equal span of output over span of input. Span of output is equal to 5 minus 5 over span of input is equal to 2.91 minus 0, and this is equal to 5 minus 5, it is 5 plus 5, which is 10 volt, over 2.1 minus 0, it is 2.1. When we divide 10 volt over 2.1, we get 3.436. This is the gain. This is the gain of our circuit. This is the gain. This is the gain of our circuit. Okay. Now we need to find the value of P. We need to find the value of P by substituting the first point. V out is equal to the gain, which is 3.436 times Vn plus P. When V out is equal to minus 5, 3.436 times Vn. Vn in this case is equal to 0. Okay, plus P. In this case, B is equal to minus 5. It means that V out is equal to 3.436 times Vn minus 5. This is the value of P. This is the final equation. We need to implement it using, because we have a minus sign here, we can implement it using a differential amplifier. Okay, we can use a differential amplifier. So in this case, we can draw the differential amplifier like this. Okay, this is the differential amplifier. This is the minus, this is the plus. This is V out. Okay. The gain is a 3.4, so we can choose this to be 34.36 kilo ohm, and this is 10 kilo ohm, this is 10 kilo ohm, and this is 34.36 kilo ohm. Again, for differential amplifier, it is very important to have this resistor equal to this resistor, and this resistor equal to this resistor. Now we have VB should be connected to the positive terminal. VA should be connected to the negative terminal, because we need VB minus VA. This comes from the bridge, Wheatstone bridge. Wheatstone bridge. delta V. The output of the Waterston bridge should be connected to these two terminals, VB minus VA. But this differential amplifier will have a gain of 34.36 divided by 10, which is 3.4 times Vn. In this case, Vn is equal, this Vn is equal to VB minus VA. VB minus VA, this Vn. So we have the equation will be V out is equal to 3.436 VB minus VA. This is Vn. Minus 5. But from where we can get minus 5? We can simply, instead of putting this ground, we can put a voltage here, voltage reference, V reference, and this should be equal to minus 5. When you put minus 5 here, it will appear the same without any gain. Minus 5, when you put it here, it will appear here at the output without any multiplication factor, without any gain. This is very important. In a differential amplifier, when this is connected to ground, then the output is equal to the input times the gain. But when we have here a V reference, then the output is equal to the input times the gain plus this V reference. In this case, V reference is negative, which is minus 5. So this is the way how we can deal with the differential amplifier. Okay, we will stop at this point. Inshallah, you will be we will get high marks in the midterm. موفقين.